is our introduction to exercise 6F on graphs and factorized cubic functions. This is a do now question from exercise 6E. It's asking us to graph or sketch the graph of y equals to 2, so bracket 2, minus x to the power of 3 minus 1. We touched on this topic earlier, as in last lesson, but it's a very unique one because it's very difficult for us to be able to identify what the graph looks like because it's in such an odd form. What I'm going to do is I'm going to try to aim to get that x value at the front. Okay? Now we can do that first, or we can find our x and y-intercepts. Let's just start by looking for our x-intercepts. So to find my x-intercepts, I have to let y equal 0. Are we okay with that? So I get bracket 2 minus x cubed minus 1. I add, equals 0, my apologies. I add 1 on both sides, get 2 minus x cubed equals to positive 1. I cube root. What's the cube root of 1? 1. 1 times by itself 3 times gives you 1. So we get that. If you wanted to, I can do this extra step here. So I get 2 minus x equals to 1. From there, I'm going to add x on both sides. Or actually, let's take away 2 on both sides. So negative x equals to negative 1. And then I get x equals to positive 1. Do I have any questions about that? Are we okay with that? Straight. So I'm going to put 1 here. Now, I've got my x-intercept. Let's go ahead and find our y-intercept. To find my y-intercept, what do I have to do? Thank you very much. Y-intercept, I let x equal to 0. So I get y equals to bracket 2 minus 0 cubed minus 1. Y equals to brackets 2 cubed minus 1. What's 2 cubed? 8 minus 1 gives us 7. Thank you very much. So I get a value, let's say up here, 7. Now, we have to try and figure out what the graph looks like. Normally, you would use your quote-unquote point inflection form in order to try and find point inflection. However, this is an odd shape. What I'm going to do is I'm going to rearrange this equation. So I'm going to do this in the bottom right just so we have enough space. I'm going to rewrite the equation, y equals to bracket 2 minus x cubed minus 1. Would you agree that's the same as if I wrote y equals to negative x plus 2 cubed minus 1? Would you guys agree it's the same thing? Yeah? Would you agree if that's the same thing if I write y equals to negative x minus 2 like that? Is that the same thing? Really? We're okay with that? All I've done is I've taken out the negative. I've still kept the cubic on the outside, so I haven't actually changed anything. But I've focused on this section here. Negative x plus 2 being the same as negative of x minus 2. From there, would you agree if I said that the cubic of a negative number is still a negative number? So for example, negative 1 cubed is still negative 1. Are we okay with that? So it's the same as if I write y equals to the negative of x minus 2 cubed minus 1. It is tantamount, the back, thank you, is tantamount to taking out that negative. Now I've done it step by step, and I would really recommend you do that step by step so you don't miss out anything. But when I take out that negative, it gives us something in the form that we're familiar with. We've taken out the negative. What does that negative at the front mean? The shape of the graph is changed. It's reflected. Now the question is, in what way? So we know our graph normally, I'm saying normally as in our graph of y equals x cubed, looks like that kind of shape. If I've made it negative, it's going to be reflected. Now my question is, in final result, the shape of our graph, does it matter if we reflect it this way or this way? No, it doesn't. So for example, if I flip this way, it's going to look like this. Agreed? If I flip it this way, it's going to look like this. Same thing. So we know it's going to change shape from something like this into something like that. Now we also have it in the form that we prefer. What is the quote-unquote, and I'm going to use quote-unquote turning point until we actually use point inflection more frequently. What is the coordinate of that quote-unquote turning point? It is, sorry? 2, negative 1. So 2 would be about there. Negative 1, let's say, is about here. So that's my point of inflection. And we know it has that shape. So I'm going to go ahead and just connect the dots, and we get something like this. There we go. Something like that. Sorry, it's going through the text. So we have our point of inflection now, and we have our intercepts. If we didn't actually find our point of inflection, I would have made the assumption that it looks something like this, with our point of inflection over there. But that point of inflection is very important. It gives us the actual shape of the graph. There we go. Does that make sense? It's a very unique kind of equation, but being able to manipulate and take out those negatives and factorize really helps. But at its core, you just need to be able to graph the cubic functions. Now, today we're going to be going through exercise 6F on graphs on factorized cubic functions on page 236. Now, the question is, you guys already know how to graph, well, hopefully, already know how to graph a cubic function when it's in that very nice form. Most of the time, it's not going to be. Sometimes, it's going to be nicely packaged as a factorized equation. So, this example over here, I've got sketch the graph of y equals x minus 1 and multiplied by x plus 2, multiplied by x plus 1. We do not have to find the turning point. We will later on, not yet. So, what's the first thing I do? If I need to sketch this graph, what do I need to do? Let y equals 0 to find my, thank you very much, to find my x-intercept. I let y equals 0, which equals to x minus 1, x plus 2, and x plus 1. Using null factor theorem, I get x equals to what, Lucas? Yep. Negative 1 and negative 2. I'm going to rewrite that over here. Negative 1 and 1. Now, the reason why I like writing it in chronological order or ascending order is because it just gives us something so we can see where those intercepts, there we go, are in reference to our x-axis. So, we found our x-intercepts. Let's find our y-intercept. So, my y-intercept, I let x equal to 0. And I get y equals to negative 1 times by positive 2 times by positive 1. Akshay, what'd I get? Are we okay with that? So negative 1 times by positive 2 gives us negative 2, times by positive 1 just gives us negative 1. So we've got those coordinates there. I'm going to draw up my Cartesian plane. Now I'm going to do points where my intercept's going to be. So x is negative 2, let's say that's there. Negative 1 is here, and let's say positive 1 is over here. I let y equal to, and remember this is my y, it's my x. I let y equal to negative 2. It's about there. Now, we've got the coordinates. Do we know the shape of our graph? Let's figure that out. So, hopefully you remember this vaguely from last lesson. If it's, and we're looking at the first from left to right, if it's a linear equation, a positive one will go up or down. Up. If it's a quadratic, it'll go down. And it's a cubic, it'll go up. So we're typically looking at cubic functions in this form here. What is the one key difference, or let's say similarity, between these two functions here? They both have a turning point. Thank you very much. In this case, a quadratic has one turning point. A cubic has two turning points. So it makes sense that a polynomial with to the degree of 4 would have how many turning points? 3. So we're working with both point of inflections and turning points. In cubic functions, it can either look like this, that kind of shape, or this shape. They both are viable depending on what form your equation's in. They're both cubic equations. But it's just something to keep in mind as we move forward. With quadratic functions, let's say I've got my axes here, and I know this coordinate here, and I know this coordinate there. How would you tell me what the turning point is? Awesome. You'd find what is the middle, or what is the average of those x coordinates. Yeah? Sound familiar? I feel like I've lost some people at the back. Does this sound familiar? Yeah? We can't do that with cubic functions for the reason being that cubic functions don't have exactly symmetrical turning points like we did in quadratics. So, we keep with that form. A quartic, or a polynomial to the power of 4, can look like this. All we've done is added an extra turning point. But let's focus on the first three. So we know it has to be in this shape here. Now that's a positive one. So we know our graph is going to be, well, is it positive? Are there any negatives? Or if I say it very explicitly, if I expand this fully, is there going to be a negative in front of the x cubed? No, there is no negatives. Now, if there were negatives, you might have to expand it. But in this case, I can tell you straight up that if we expand it, x times x by whatever it is, we get x cubed, which is a positive. So we know it's a positive form. So based off that, we know our graph looks like this. I can kind of connect the dots. I'm going to connect them like this. Now, are we sure that's right? It could be wrong. It could be right. So that right there could be our turning point. It could also not be our turning point. At this stage, we're not equipped with the skills to tell us whether that's the answer or not. But that is the general shape we're going to be working with. Do I have any questions about that? No? Okay. So that's one way to find this. We can determine what is the general shape of this graph by referring back to this table and being like, okay, a cubic function goes up first or down first. What if we don't want to do that? What we can do instead is sub in a value of x. Because right now, and if I'm being very artistic, we could have a function that looks like, oh gosh, looks like this. It could look like that, or it could look like something like that, I don't know. What we can do is we can remember that it's a cubic function and we can substitute values of x. If I was to substitute a value for x, as in, let's say x equals 0, we get y equals -2. What if I was to put in x equals to -1.5? Now, this is something that you might want to do using a calculator if you are using a calculator. But at this stage, if I was to substitute x equals -1.5, I would get a line, a point somewhere on this line here. That's where x equals -1.5. From there, it'll tell me, let's say I put that in, and it tells me that that value gives me something up here. In which case, I know that my line goes up here and then back down. Does that generally make sense? So there are two different methods. I prefer the one where you refer back to the table, but they both work. As long as you follow that same rhythm in terms of a cubic function having that shape, and you have those coordinates and follow those points there. There's two more notions I want to go through today. So sketching the graph of y equals x squared multiplied by x minus 1. What is the difference between this question and this equation over here? Say again? Marissa?
It's not factorized.
It is not. It is factorized, but it's factorized in a different way. We have a repeated factor. So instead of having three different factors like x minus 1, x plus 1, and x plus 2, we have an x minus 1 and we have an x. Now that x is repeated. So we know that x, and x minus 1 are three factors, but they're only two different factors. So what I'm going to do from there is I'm going to draw this graph here. Using null factor theorem, can you guys tell me straight up what is my x values? What are my x values? 0 and +1. Now we know it's 0 because if I use null factor theorem, ignore x minus 1, we get y equals x squared, which we know to be just 0 as a x coordinate. So from there, I've got that. Is it a positive or negative cubic? It's a positive. So I know it has this kind of general shape. I know it goes up first, then back down, comes back up. Now, let's find my y-intercept. So y int, I let x equals 0, I get y equals to 0. 0 times by whatever it is, it has to be 0. So I know that it goes through this point here. Does that make sense? Yeah? Okay. Here's the thing about repeated factors. If it's a repeated factor, it goes and repeats, it's kind of symmetrical on both sides. And I'm going to draw this graph out so you can see what I mean. You can see that for when x is x, so y is x squared, it's symmetrical and it goes up and then comes back down over here. So if it has a repeated factor, that means on both sides, it's going to be the same, either both negative or both positive. You cannot have, for example, something like that, because that is not symmetrical. For that repeated factor, where, for example, x squared, that is the same on both sides. That's something to keep in mind as you're moving forward, but the core of it is being able to find those x-intercepts and then finding, based on those, on the general form of the cubic function, connecting dots and getting that graph. Last one. Oh no, that's it. That's all I want to go through, my apologies. There are other situations. For example, if you have a function where you only have one x-intercept, so let's say you have two factors where one of them is a linear equation and the other one is a quadratic equation that you can't actually solve. Maybe you use discriminant to find out that you can't actually solve it, in which case you just draw as is using that one x-intercept. Do I have any questions? Can I get you guys started working on exercise 6F? I'll come around if you have any questions, otherwise let me know.